So if you have a basis, then any sublist of it is going to be independent, and any list that contains it is going to be a spanning set. But we can expand on this. So one way you can expand on this is if you look at the collection of all bases, right? The collection of all bases includes all collections of independent sets and is included in all collections of spanning sets, right? We can also expand on this in other directions, though. So, for instance, with theorem 231, we have that any spanning set contains a basis, and every independent set is contained in some basis. So instead of starting with a basis and going in either direction, we can start on the either side and work towards a basis. So for the first one, every spanning set contains a basis. And the idea, and we'll see this reflected in the proof, is that you can just winnow away extra vectors until you get something that no longer has any linear dependence, and then it'll be a basis. And the other one is that every independent set is contained in some basis. Or the way that this is often phrased is people say extends to, because in practice you might have a few vectors that are independent, and then you say, well, let's make a basis out of this by extending it to some bigger thing. Okay. Turns out that the second one is much more difficult in the case when V is infinite dimensional. So we're going to skip that. We'll only do it for finite dimensional, and you'll see Axler does the same thing. He avoids the infinite dimensional case. So let's look at the proof. So for the proof of the first one here, suppose we have that V is the span of B. So B is some list. And then without loss of generality, so if you haven't seen this before, this is without loss of generality. Whoops. None of the VJs are equal to 0. And so the reason why I can make this additional assumption is because if there's a 0 in there, then we can just delete it and take B to be the new list obtained by deleting any zeros. Okay. And you'll notice also I'm glossing over the case when V is the trivial vector space, which is the only situation that you have to worry about getting an empty set here. So, but that case is so easy though that I'm not going to worry about it. So this without loss of generality expression right here, this just means I can make this additional assumption, and it's justified essentially by ruling out cases, or just adjusting notation or meaning slightly. It means I'm not cheating, basically. Okay, so let's see. So now this proof is going to proceed by a process, kind of an algorithm. So what we're going to do is we're going to say for each V in the list, so starting at the second one, we're going to check if Vj is in the span of V1 to Vj minus 1, the previous item from the list. Okay, so if it is in there, then we delete it. Let's actually move this down below so it looks almost like a computer program. If not, so else. Continue on to check the next item in the list. Okay, and so now whenever you have a proof that operates like an algorithm like this, as an iterative process, you need to check, you need to make sure that your process ends, and that when it ends, you have what you want. Okay, so in order to see that we're going to get what we want, notice that since any deleted vector is in the span of the others, because that's the only time we delete something, the span of B doesn't change. So in other words, even as we delete vectors from the list still spans all of V because we only take away things that are redundant. Okay. And then the process has to stop. And it stops at the step when J is equal to N. And that N here that I'm referring to is this one that we had from back at the very beginning. Right, so the length of our spanning list. And so at this point, we've constructed our list to ensure that no vector is in the span of the previous ones. By which I mean the vectors which appear before it on the list B. Okay, so then by the linear dependence lemma, which is number 221, the resulting list B is independent. And since we already saw that the span of B is going to be equal to V throughout the entire process, that means we have a basis and we're done. Okay, so the other one is, what if we start with an independent set? And so I said we're just going to look at the case if V is finite dimensional. And so if it's finite dimensional, then we can find a finite spanning list. Man, I'm so used to saying spanning set. This is throwing me for a loop with this Axler book here. Okay, so V is going to be in the span of these guys. Oh, let's stick with the last one being M. So V1 through Vm, as I have in my notes. Okay. So let's see. So suppose we have our independent set. I'll call it L0. And so we've got K things in there so far, U1 through UK. So let's start under the assumption that we've got this independent set. Okay, we're going to do another sort of algorithmic recursive or iterative procedure type of proof. So for each non-negative integer j, if the span of Lj is not equal to V, then there exists something in the complement. So there exists something, we'll call it UK plus 1. And it lives in V, but not in the span of Lj. Okay, right, so if the span of Lj is not the whole space, then pick something that's not in the span of Lj. Call it U sub k plus 1. Okay. And then we define our new list to be the previous list, and then we tack on this new element on the end. Okay, so repeat this process. So check to see if the span is everything. If not, then pick something from the complement, throw it in. Did we get everything now? If not, keep looking. Okay, so now notice that each of these lists that we produce, LJ, is going to be independent by the dependence lemma, once again. And that's by the contrapositive of it, more or less, because no uj is in the span of the others. Right? So that's by construction. And then we also have to note that the process terminates. And this is where we need the finite dimensionality. Oops. And this is just because we know that we have a spanning set of length m, so LJ can't have length greater than m. And that's by our lengths of lists lemma. God, that's too many L's. Okay. And that does it.